In section 6.3, we'll be looking at logarithmic functions, and in particular we'll be focusing on mostly just the properties of logarithmic functions, and in the next section we'll start to look at doing calculus. So in this section it'll mostly be things that you've perhaps seen before in a pre-calculus class, but we're going to get it ready so that we can start doing calculus on it. So the basic definition of a logarithm is to think of it as the inverse of an exponential function. So for instance, if f of x is equal to b to the power of x, then the inverse, f inverse of x, is equal to log base b of x. So this has the basic property that we can take an equation of the form log base b of x equal to y, and interchange it into an exponential form, x equals b to the power of y. Sort of interchanging the input and the output variables between these two sides of the implication. So we'll call this the logarithmic form of the equation, and we'll call this the exponential form of the equation. Okay. So let's practice this idea a little bit. Take for instance the equation log base 3 of something is equal to 4. So if I were to interchange this into an exponential equation, we can try and figure out what belongs here inside that logarithm function. So in this case we have a base of 3, and if I raise that to a power of 4, that will tell us what goes inside the function. In this case we see 3 to the power of 4 would be 81. So therefore log base 3 of 81 is equal to 4. In this one we've got a base missing. So for instance, if I want to say log of what base of 5 is equal to 1/2. So again, we can think here some number in our base raised to the power of 1/2 will equal to 5. So we can think now 1/2, we know that's like the square root. So therefore what we're looking for has to be 5 squared. So therefore we would see that log base 25 of 5 would equal to 1/2. And we can verify that that's the same as saying that the square root of 25 is equal to 5. And then finally here we're given log base 10 of 0.0001, and we want to figure out what is that equal to. So again, let's think of this in its exponential form. 10 raised to what power is equal to 0.0001. And the idea here is that 0.0001 can of course be written as 10 to the power of -4. And therefore our log base 10 of 0.0001 has to equal to -4. And of course, because the logarithm and the exponential function are inverses of each other, it inherits some properties that any inverse functions share. So if I do the composition of log base b composed with b to the x, we know that this will equal to x for any x that belongs in the domain of b, or of b to the x. So of course we know b to the x can take on any value of x, so this will be true for any x. So any real number x. On the other hand, if I've got b raised to the power of log base b of x, we know in this case our logarithm here will only be positive values inside. We can only take the log of positive values. So this will only be true for x greater than or equal to 0. Or actually, I should say only strictly greater than 0. since here log of 0, log base b of 0 is undefined. And here's a good way to visualize the relationship between an exponential function. So for instance, if I've got the function b to the power of x in the blue graph, we know that if I reflect that in the line y equals x, we get the graph of log base b of x. And of course we see that here because b to the power of x is always going to be above the x-axis, the log base b of x will always be to the right of the y-axis. So here you see that's why the x values here are always going to be greater than 0. And depending on the base b, we could have a variety of different shapes. For instance, we notice that as the base b gets larger, the graph of the logarithm tends to get a little bit flatter. So it tends to rise less rapidly. Here are some basic properties of logarithms. Of course, these properties can be proved pretty easily using what we know about exponential functions. But let's just go through the properties here. If I've got a product, x times y, inside of a logarithm, that can be expressed as the sum of log x plus log of y. If I've got the quotient x divided by y inside of a logarithm, that can be written as the difference log base b of x minus log base b of y. And if I've got the power x to the power of r inside the logarithm, that can be written as r times log b of x. These will become useful, of course, much later in the next section when we start performing calculus on logarithms. In other words, we might find applying these properties to be a handy way to simplify a logarithm before we take its derivative. Let's practice those properties a little bit. Say, for instance, I've got log base 4 of 2 plus log base 4 of 32. Well, we know that this can be written as log base 4 of 2 times 32, which is log base 4 of 64. And I can actually evaluate this because I know that 4 raised to the power of 4 will give me 64. How about this one? We've got log 2 of 80 minus log 2 of 5. Well, we know that this would be the same as log 2 of 80 over 5, which simplifies to log 2 of 16. And again, I can evaluate this because I know that 2 raised to the power of 4 will equal to 16. What happens in the logarithm as x approaches infinity? Well, what we've noticed is the graph of the logarithm will tend to get larger and larger and larger. And so as x goes to infinity, log base b of x also goes to infinity. What happens as x approaches 0 from the right? Well, in the graph of log base b, if we remember we've thought of this as the inverse of the exponential function. So we know that the exponential function tends towards 0 as it goes to the right. So the same thing happens here, that as x approaches 0 from the right, the graph of the logarithm will go to negative infinity. So with that idea in mind, what can we say about the limit as x approaches 0 of log base 10 of tan squared x? So we know that tan of 0 is actually 0. So tan squared will be approaching 0 from the positive side. As x approaches 0 from either side, because it's squared, right? We know that it'll be always a positive value. So this would be the same as taking the limit as x approaches 0 from the right of log 10 of x. So we can think of it as the limit as, say, t approaches 0 from the right of log 10 of t, which will just be negative infinity. An important type of logarithm that we'll focus on for a moment will be the natural logarithm, which we're defining as the log base e. So the special notation ln of x denotes the log base e. So of course it has it inherits all the properties that we've discussed so far about logarithms, in this case particular to the base of e. So ln of x equals y if and only if x equals e to the power of y. That's just the interchanging between its logarithmic form and its exponential form. We know that ln of e to the x is equal to x. There we're just doing the composition of logarithm of the exponential. And e to the ln of x is equal to x as well. So this again would be for any x, for any real number x. On the other hand, this would only be for positive x, since we need to only consider positive x inside the logarithm. Let's practice this basic idea by solving some equations. If I want to, for instance, solve the equation ln of x equals to 5, well, of course, we know that this can be written in its exponential form. E to the power of 5 equals x. Hence, we've got our solution for x right there. If I wanted to get an approximate value here, you can type that into our calculator. Of course, every scientific calculator will have a button for e to the x. So in this case, e to the power of 5 gives me something around 148.41. How about this equation here? E to the power of 5 minus 3x equals 10. So again here I can interchange this into its logarithmic form, which will look like ln of 10 equals 5 minus 3x. And then solving for x in this equation, we would have 3x equals 5 minus ln of 10. And then dividing the 3, I get x equals 5 minus ln of 10 divided by 3. So here we have an exact answer, and again we can use our calculator to approximate the value here. 5 minus ln of 10, and then divide by 3, we get something around 0.899. Okay, so we see here just interchanging between the logarithmic and the exponential form allows us to easily solve these basic types of equations.